Okay, let's get started. So, see the bar there? Get rid of that. So today we will start talking about buffer overflow, especially stack-based buffer overflow, and we're going to spend several weeks on this. We're talking to easy version of it, the much more complicated version. So stack-based buffer overflow is also called a sequential buffer overflow in some literature. That's because the classic box is you have a string copy or memory copy that sequentially copy something onto the stack and overwrite something onto the stack, also including the return address on the stack. So it's sequentially. So that's why it's called a sequential buffer overflow. So we will talk about a little bit the history of buffer overflow, what kind of information safe functions needs to run, then the application binary interface or the say calling conventions for 32-bit and 64-bit. We talked this a little bit in the computing system class as well, and also local variables. So today we will see multiple examples that how we can overflow local variables. So I will show you one or two examples, then you are going to do one or two. And also in the homework, there are more challenges for you to hack. So next week, we will talk about how to overflow the return addresses. So return address is something on the stack, but it's a return address. It's where your function returns to. So it points to a code. So it's a code pointer. So if we modify that address, then we can return to any place we want. Or we can even inject some code there and make the CPU to execute our code. So that's what we will do next week. Then we will say how we can return to a function and also give the function different parameters at a 32-bit next week. We're not going to do 64-bit next week because it requires a different technique, which we will talk about after the midterm. So the objectives here, you need to understand how stack works for Linux, for x86. This is the CPU we're talking about. Then you should be able to identify some obvious stack-based overflows at a source code level and also at a binary code level. When you are trying to hack something, you do not necessarily always have the source code. Most cases, especially when you're an attacker, you only have the binary code. Sometimes you don't even have the binary code. You have a black box there, you keep sending something, and you get some feedback, and use that, you can infer the code of the program. Then you will learn how to exploit such vulnerabilities. We're taking multiple steps to do that. A little bit history of buffer overflow. So this stack-based buffer overflow is discovered back in 80s. So security has been a very old topic, maybe thousands of years old, right? So thinking about 2,000 years ago, people talking about security, they're talking about how to secretly transmit messages in walls, right? So that kind of security is meaning about data security. How do you transmit some data from one party to another party? Even now, what we're doing, a lot of what we're doing is still data security. You open your browser, you visit a website, and also, for example, in this room, your laptop connects to the Wi-Fi access point. The Wi-Fi access point connects to another university router, then eventually connect to the website that you want to visit, right? But you don't want anyone else in this classroom know which website you are visiting or what kind of content you are, at least what kind of content you are exchanging with the website. So that's why you use HTTPS, so everything is encrypted there, right? So that is mainly data security. So a lot of security we're doing is data security. Before 80s, before the discovery of a buffer overflow, mainly is data security. Then from the 80s, discovery of buffer overflow, we realize system security, software security becomes a new thing. the software we're developing, they could have all kinds of bugs. Now we have many, many different kind of bugs at different levels. But this buffer overflow, a very, very powerful one, was discovered in 80s, and it started, I can say it started almost everything, right? So this buffer overflow also played a very important role in the first felony conviction in the US under the Computer Fraud and Abuse Act. So in 1988, a student, Robert Morris, at Cornell University, he developed the famous or infamous Morris worm, and that one was distributed via internet. And at that time, internet probably only had hundreds or thousands of computers, of nodes. Then his worm, his virus, took down maybe 80% or 70% of the computers that time. Okay. And he leveraged some stack-based buffer overflow there. Okay. So there are services running on different computers. They read input from the internet, and the read input function has a buffer overflow exactly like what we teach in this class. So at the end of this buffer overflow module, we are going to look at this Asian bug, how he exploited that. And Robert Morris right now is a professor at MIT. He made huge contributions to computer systems, computer security. But before all of that, he made this virus, made him very famous or infamous that time. But still, that time, not many people really know how to exploit this. There were no well-documented materials teaching people how to do that. So until, I think, the right-hand side here, this is an article published in 1996 in a magazine called Frank. So that's a digital magazine. We still have that. So that's a hacker magazine. So someone under a pseudonym Alpha1 published this very, very important paper called Smashing a Stack for Fun and Profit. So this is the first time there's a well-written document explaining to the world how do you exploit this vulnerability. Okay, so this is a must read for everyone. So this will be your homework to read this. So Alpha1 obviously is a pseudonym, but if you just Google, you can find who is the real guy behind this. So even today, stack-based buffer overflow is still a very serious software security problem, even after almost 40 years. We haven't eradicated the problem. There has been a lot of attempts to address the problem. Our research lab also have some papers published this, but still, we are still facing the problems. And in this class, you are going to say how to exploit it, what kind of defenses we have been deployed in the last 40 years to defeat this, and why they work, why they don't work. And one of the main reasons they are not really eradicated in real world is because some of the defenses are very, very computational expensive. Okay, make your computation very slow, so it doesn't really make sense to deploy it. So security is a trade-off. Security and performance is a trade-off. You add more security features, your system runs slower. So sometimes the asset you are trying to protect is not worthy of protecting, but performance is more important. So here you can see that stack-based buffer overflow is still ranked number 14 on this list. This is the latest list released by MITRE in 2025 of the most dangerous software weaknesses. However, you can see number 5 is also related to this, out-of-bound write. So stack-based buffer overflow is actually one special case of out-of-bounds write there. So in a more general form, you do not necessarily overwrite the stack, you overwrite other places. So number 5 is still very popular. You do see many other popular software weaknesses, but they are not necessarily for binary software. For example, the first one, cross-site scripting, that's obviously web-based. The second one, secure injection, is obviously for database. So those are not things we don't cover in this class. We only cover the binary ones, like let's say out of bound right, use after free. We will talk about this after midterm, out of bound read related to out of write, and the code injection. We're going to do it next week. This one, classic buffer overflow, and also stack-based buffer overflow. That's what we're talking about in this week and maybe 2-3 weeks. We have several modules for that. Okay, so now we need to understand for any C function or even C++ function, what kind of information we need at runtime so we can actually call that function, right? So, of course, a function, first of all, you have code. You write the source code, compile to binary code, but binary code are machine instructions. So, code, first of all. Then, when you develop a function, sometimes you give it parameters, right? Some functions do not need to take parameters, but you can give parameters. And the C functions we have one return value. Of course, C function literally they can return more values, but there is one thing called a return value. If you want to return more things, you need to send a pointer to the C function. Then that function can change, dereference whatever at that pointer, change that value at that memory address. So technically, those can also be considered as return values. We just do not call them return values. Then a C function can refer to global variables. Also, their own local variables. There could be some temporary variables as well, but we can consider them same as local variables. Also, there is a return address. This is not specific, not explicit when you program a C function. But obviously, when you program a C function, you make a call to a C function. After you call that C function, you are going to execute the next statement after the call. So which means the control flow goes to the function you called, then come back to the next statement after the call instruction, right? So that is a return address there. Also, to implement all of this, we need a function frame pointer and also the previous function's frame pointer. We're going to show more examples of those later. Let's start with the simple ones. Global and local variables. Variables that are declared inside a function or a block, they are called local variables. So they can only be used by statements inside that function or inside that block. Okay? So they cannot be accessed by other functions in other files. They cannot access that. Then there are global variables. They are defined outside any function. So this is very similar to any other language anyway. So then global variables will hold their value throughout the lifetime of the program, and they can be accessed inside any function defined for this program. Then we have parameters. Parameters, they actually can be stored at where local variables are stored, but for 64-bit versions, we also use registers to store formal parameters to make things a little bit faster. We will see more examples of that. So this is the first example we are going to say today. So we have a very simple C program. There is a main function. Main function takes two arguments. The first one, argc, is an integer. That's a number of command line arguments you give when you run this program. Then there is an array of strings. So those are each command line arguments. And the very first command line argument is the name or path of the program itself. Then the other arguments are passing to this program. We have a local variable L underscore I initialized to integer 10, another uninitialized local variable L underscore U there. Then we have a printf to print out two global variables address, and those global variables are defined left-hand side. The first one is actually a pointer, it points to a string, and the string itself is hard-coded. So here we have two different things. We have the string itself. The string is probably 25 letters. The string itself should not be changed. So it goes to the read-only data section. Then we have a pointer, which is a global variable, g_I. That's a global variable, that's a pointer, and that points to the address of the string. However, the value of g_I can be changed, right? It's a global variable. You can change the value at runtime. Then we have another uninitialized global variable, g_u there. Its value is uninitialized. However, in C, we talked about this last week, C standard requires all of the uninitialized variables to be initialized to 0. So technically, that one will have value of 0 when your program runs. We have another function called func. Func takes one parameter, also an integer, we call it p. It also has two local variables. They have the same name as the local variables we have in the main function. The func will print out the parameter's address, not the value of the parameter. It will also print out the address of those two local variables. Main function will also print out the addresses of two local variables and also call the function func. Right? So if we run this program, we are expecting to see just the 7 addresses, right? So let's run this program first. See what we get. So when we run this program, the outputs are just 7 lines. The first one is the global variable gi's address. You can see the address is 56 something. The address space is from 0 to 8Fs, somewhere the lower half. Then GU is at a little bit higher address than that, but they are still close to each other. Then we have a local variable, the li from the main function. It's at a very high address, right? The address space, the highest address in this address space is just 8Fs. So here we have 4Fs at the highest 2 bytes. So that's a very high address. Then li was defined before lu. Okay. So they are on stack, and li has a higher address than lu, as you can see. li is at 8C, and u is at 88. 8C and 88. So obviously, 8C is at a higher address. So the stack goes from higher address to low address. The first defined local variable has the highest address. Then we have the next defined local variable, which has a lower address. Then the main function calls func. Okay? Func print out its own local variables, and you can see they have an even lower address from 8C to 5C to 58. Then obviously there are some data in between. Okay? So compilers will generate many instructions to put data on stack, and those are the data you cannot see here, but those are the data we want to attack. Then we also have the local, the parameter for this function. You can see this address is actually higher than li and lu. So the parameter is at a higher address at both local variables, but obviously it has had a lower address compared to the local variables of main function. Okay, so that's the 32-bit version of it. The 64. Oops, what's going on? Let's go back to challenges. It's smaller. The 64-bit version of this is similar, except that the address space is much bigger. Here, we're looking at a 64-bit address space. Of course, the current system, we're not really using full 64-bit. So you can see that the stack is not like at super high address. It's not at FF. It started with 7F. But global variable is still at somewhere middle in the address space. Mains local variables have higher address than func's local variables, and the parameter in func has a higher address than, so this one, not really, see here. So this one, the P has a lower address than the local variable of those two. So the reason is, in 64-bit version, the parameters are not really passed through the stack. We actually use register to do that, but you obviously cannot print out a register's address because register is not memory. There's no address. So here in the C code level, I asked to print out that. Then the compiler will create another local variable to do that. That's why it has a lower address. So if we do not print out that pin's address, then we will not even use that memory address. So okay, so where do we store such information? Obviously, we only have two places to store them, either on the memory or in some registers, right? So code, as we saw last week, they will go to the elf files.txt section, and when at runtime, where is code? Obviously in the memory, right? The parameters, they can be on the stack, and they can also be on registers. For 32-bit, they are mostly on stack. There are some calling conventions. We can put parameters in registers to make things a little bit faster, but there are only limited numbers of registers for 32-bit. So we do not do that very often. 64-bit, we have many, many more general registers. That's why we use registers to pass parameters. However, still, we only have limited numbers of registers. But our function can take unlimited numbers of parameters, and also can take a very long list of parameters, but also literally unlimited numbers. Okay, then, so after a certain number, we still need to use a stack to pass the value, not use registers. Return value usually goes to the register EAX or RAX. Global variables go to .bss section for uninitialized ones, .data section for initialized ones. Local variables usually use a stack. We can also use registers to do that if we have enough registers. Temp variables, the same. Return address are stored on the stack. Okay, stack is memory. So that is very dangerous because return address is a code pointer, and you are saving a code pointer onto the stack, which can be overwrite. The function frame pointers are stored in the register EBP and the register RBP. And the previous function's frame pointer is also stored on stack. We're going to see examples of that. Okay. So stack is a basic data structure. You probably know this in your data structure class. And hardwares, they have native support for stacks. All the architectures we use, they have instructions to support a stack. Usually, our stack starts at a higher memory address, then grows down to a lower address. But some architectures, they do support stacks in reversed order. But the system we are using in this class, and also your laptop, your phone, your tablet, everything. They are using a stack from a higher address to a lower address. The functions, they can push values or values in registers onto the stack. Then they can also pop values from the stack. So from data structure point of view, stack is a first in, last out data structure. Whenever you push to the top of the stack, and when you pop to the top of the stack, which is the last element of the stack. In x86, 32-bit and 64-bit version, there are some special registers to support stack. Okay. Also, other architectures, they have special registers. So you need to remember those two registers. One is called ESP, another one is called RSP, 32-bit version, 64-bit version. So ESP and RSP holds the address of the top of the stack, which means it points to the last element you pushed onto the stack. Okay. A register points to that, which means the register has the address of that. Okay. Then instructions we talked about last week, a push and pop instruction. When you push something, you are storing something onto the stack. So we can divide this into actually two steps. The first step is to decrement the stack pointer, which is ESP or RSP. Okay. Then we are going to store the value to ESP or RSP points to. That's it. Okay. We do not. This is the order we are going to do it. Okay. This guarantees that ESP and RSP always points to the whatever you just pushed. Okay. It's not going to push we're not pointed to an empty place. The reverse operation of push is pop. Pop will just store the value at the location pointed by the stack pointer, ESP or RSP, to the register, or sometimes it can be memory as well. It will copy that from a memory location. The memory location is pointed by ESP, RSP. Copy that to your register or memory. Okay. After that, it will increment the stack pointer. Okay. So in 32-bit machine, obviously, the push or pop will increment or decrement 4 bytes. Okay. In 64-bit machine, it will be 8 bytes, because when you push up RX stores 8 bytes of data, not 4 bytes of data. Okay. So those are the basic operations, push and pop. There are more instructions, but I have some animations to help you understand this, because this is very, very important. Let's say this is a picture of the memory, and this is high address, this is low address. So right now, we are about to execute the instruction push EAX or instruction push RAX. And the ESP or RSP points to here, which means this is the top of the stack right now. Okay? The stack goes from high address to low address. So on stack, there are already some values, Z, Y, and right now, ESP, RSP points to X. So now we are going to run this push instruction. What happens is after we execute that instruction, the value in EAX will be stored at the address lower than X. That's it. Then ESP or RSP points to here. Okay? As simple as that. So pop is the reverse operation. Now we have ESP, RSP points to X. After we pop, the value X will go to the register EAX or RAX. Then ESP, RSP value will increment. So now it points to value Y here. However, at this memory location, we still have value X because no one cleared that. Okay, this instruction will not clear this. Okay. The next instruction that will influence stack is the call instruction. Here we have an indirect call example, call EAX. Indirect call here means the target is not predetermined. Compiler didn't determine the target. An indirect call is called to a specific fixed address. So here the stack, what we have is Y, Z, Y, X. And here we have the instructions. And this is low address, this is high address. We just have an instruction of push 1. We are about to execute the instruction called EAX here. So EIP or 64-bit RIP, this register will have the address of the next instruction to be executed. Okay? So when it has this, means this instruction has not been executed yet. We're about to execute this. Then after this, we also have another instruction, pop EBX. So the call instruction does two things, very simple things. The first thing is to push the address of the next instruction onto the stack. So the current instruction is called EAX. The next instruction is pop EBX. So the address of this instruction will go to the stack. Okay? So the stack will look like ZYX, the address of pop EBX, and the ESP or RSP points to here. Then it will move the destination's address to EIP or RIP. So the destination's address right now is in the register EAX. So then we will start execution at where EAX points to. Okay. So after that, we are going to execute. Well, obviously, we're not executing here. We're executing somewhere else. And that piece of code may also be manipulating the stack, right? So they were going to push a lot of things. But eventually, when that function returns, it should guarantee that ESP, when it returns, it will point to this place. The reverse operation of call is obviously return. This instruction is also very simple. It will pop the top of the stack to the register EIP or RIP. That's it. So ESP, let's say the stack looks like this, ZYX. EIP points to the return instruction. We are going to execute the return instruction. The return instruction will pop whatever ESP points to. ESP points to X. So the next instruction we are going to execute is at address X. Okay? So we're not going to execute the next NOP instruction. Instead, we're going to address X. Okay? So this one will not be executed. So both call instruction, return instruction, and also actually push and pop instruction, they will use the ESP or RSP registers implicitly. It's not really in the syntax. When you look at the syntax, push EAX, you do not say ESP or RSP there, right? Also, the return instruction, they will also use the value stored there as well. Okay, not only the register, but also the value stored there. And this value is supposed to be stored there by a previous call instruction, as you can imagine. And we do have several other instructions. One is called the enter, another is leave, and the enter is equivalent to 3 instructions, push EBP, move ESP to EBP, then subtract some numbers from ESP. So those 3 instructions, they are so popular at the beginning of our functions. Compilers always generate that. Then Intel or AMD decide to just design a new instruction to replace those 3 instructions to make things a little bit shorter, and that is enter. Then what do they do? Let's say before those 3 instructions or before enter, our stacks look like Z, Y, X. ESP points to X. Then the first instruction we execute is push EBP. Of course, EBP can also be RBP, the same thing, which means we are going to save the register EBP's value onto the stack, okay? Then after that, ESP will point to here, okay? Then we are going to move ESP to EBP. Then EBP points to here, okay? Both EBP and ESP points to here. Then we subtract some numbers from the ESP, so ESP moves down to point to here, okay? I will have more animations later, okay? So, but you can see that what we are trying to do here, while we are subtracting some numbers from ESP and get more space here, okay? Any guess why we're doing that?
Maybe try to add some piece of code or some data, like to input some data.
Okay, so here is not really input data, but this is a way to reserve local variables. So your local variables can go to this area. Then you can refer your local variables as EBP minus something. Okay. Then leave is a reverse operation of that. Basically, it's move the EBP's value to ESP, then pop EBP. So this happens at the end of the function. We can skip this for now. Later we have more examples. Yes?
You mentioned something about keeping data in the middle.
That's a very good question. We will talk about that maybe in 3 weeks, actually, and we are going to defeat canaries as well. So canary usually is placed between a buffer and the return address because it's trying to protect the return address. It will use other instructions to do that. So those instructions I just showed you do not necessarily do canaries, but it will be in that region. Yeah. So functions, they obviously need this stack. So each invocation of that function, of a function, will need its own stack. Not only a software implementation of a function need a stack, an invocation of that need a stack. A function can invoke itself, can call itself, right? That's a recursive function. So for a recursive function, every time it calls itself, there will be a stack. Then obviously the value of ESP, RSP will change throughout the execution of the program. Frame pointers, that EBP, where the EBP points to, that actually indicates the start of a function's, this invocation's function frame on the stack. I will show you more examples later. This one we can skip. Okay. Now we're going to look at several calling conventions. When you program in C, you do not really care for this. But if you develop a compiler, you change the C code to binary code, this is what you care about. This is part of application binary interface, ABI. When you program in C, usually you care about API, right? You care about what kind of a C library function you call, what kind of interface you provide to others to call your C function. But to make sure your C program compiled to the binary code and the binary code can be executed on different platforms, the binary code can be called by other functions generated by other compilers. At the binary level, we need to make sure we speak the same language, and that is the ABI, right? So it determines what should be stored onto the stack and in what order we should store on the stack, and whose job it is to store such information. There are many different APIs, and obviously we're talking about Intel here, AMD here, and x86. Different architectures, obviously the API will be much different. So in 32-bit Linux, the API we use a standard C declaration API. So you have a function, the function calls another function. The first function is called the caller, then the function be called is called call-e. And this is what each of them supposed to do at a binary level. Okay. Of course, compiler does this for you. You do not code this part. Okay. The caller will push the arguments onto the stack. Use the push instruction. And the compiler will first push the rightmost argument, then the second rightmost argument, then eventually the first argument. So it's in right to left order. We push the arguments. Then the caller will execute the call instruction, which will save the next instruction's address onto the stack, then do an unconditional jump to the target, right? Then where is the target? The target will be the very first instruction of the call-e, the function you are trying to call. Okay. Then the call-e job include first will push the previous function's frame pointer onto the stack. Okay. The frame pointer is EBP or RBP. Okay. And we enter a new function, the call-e. So the call-e is going to use that register, EBP or RBP. But EBP, RBP at this point has the value, the frame pointer of the previous function. So we have to store it somewhere, save it somewhere, so we do not lose that information. So we store that, we push that to the stack to store it. Then it will set up its own new frame pointer by moving ESP to EBP. Okay, because we just pushed that. So the latest address will be in ESP, then we just move that to EBP. Now EBP has the current function's frame pointer. Then we are going to create some space for local variables, subtract some number from ESP. So those are the three instructions we just saw. Then it will just execute its code. The code may use a stack, may not use a stack, may call other functions, right? The call-e may call other functions. Then that time the call-e becomes a caller, and the call-e has to follow the caller's convention here. Eventually, when call-e is about to return, you need to make sure that the stack is consistent, which means when it returns, the caller can keep executing. Okay? The caller still says those registers have the correct values, so you can keep executing. Also, the call-e needs to put the return value in the register EX or RAX. That's it. Okay. So those three instructions we saw just now, they are usually called the function prologue. But of course, function prologue means at the beginning of the function. You can also add other instructions there. They will also be part of the function prologue. Then the function epilogue, we have those three instructions. In addition to the move EBP ESP to ESP, pop EBP, we also have the return instruction at the end. Okay, so that's the beginning of the end of this calling convention. Okay, this is not the only calling convention, but most of the C programs functions are compiled with this calling convention. So go back to the previous example. We have the main function. Main function calls func. Okay, this is the disassembly of the main function. The main function at this point calls func. Func takes one parameter, right? And this is a 32-bit machine. So how do we pass parameter? Stack, right? So we push the value onto the stack. in right to left order. So here we only have one parameter, so we just push down to stack. So in this case, we are going to push. So if you, let's go back to the C code. The C code here, the main function will first call 4 printf functions, which we don't care about. We care about this one. We are going to call func with the parameter 10. So this is a hard-coded parameter, okay? So that's why we need to push 10 onto the stack before we make the function call using the call instruction, right? So then you can see here, before that call instruction, we have a push instruction, okay? And the push instruction, you push a value, which is A in hex. That is 10 in decimal, right? So we are pushing 10 here, then we call this function. Then the next instruction to execute will not be this add. Instead, it will be the function's first instruction, which is this part. Okay, and the func function actually only has, I don't know, maybe this is 20 lines of 20 instructions. Okay. At the beginning, you can say we have push EBP, move ESP to EBP, subtract something from ESP, okay? Exactly as what we discussed before. Then it makes 4 or 3. It makes 3 function calls, okay? So those 3 function calls should eventually map to 3 call instructions. And we can find them here. This line, we have a call instruction. This line, we have another call instruction. Here, another call instruction, right? We have 3 call instructions, and we are calling printf there. And for printf, let's say the first time we call it, how many parameters are there? 1? 2, actually. Okay, 2 parameters. The first one is a string. The second one is an address, okay? That ampersand is for to get the address of a variable. Okay, the first one is a string. So do we really push the string onto the stack, the string itself? No, right? So string is stored in read-only data section. What we are pushing here is the address of that string. Okay. Then the second one is a value. The value is the address of that local variable. So if we can say the first function call here, before that we say 2 pushes. Okay. The first one is push EAX. Another one is push 700 in hex. Okay. So what is EAX? EAX is actually the address of the local variable. Okay. So why EAX is the address of local variable? So you need to look at this instruction here. Let me use do I get? Oops. Okay. Cool. So here we're looking at these 4 instructions. Oops. The first instruction is LEA. We talked about this last week. Load effective address. Okay. This instruction will give you an address. The address is EBP minus C in hex. Okay. EBP is somewhere, points to somewhere on stack. Minus C will be a little bit lower. And that is the address. We're moving that address to register EAX. Then we push the address onto stack. Okay. So which parameter is that? The first one or second one? Yeah, the second one, right? Because we push parameters from right to left. Okay, there are 2 parameters. We push the second one first. Then we push the first address. And the first one is a hard-coded address, 700. So that is the address of the string. It's hard-coded. Okay. So that is this example. Okay, so now you can have a basic understanding of what does the stack look like. This is for 32-bit. We first, at the very top, we have the arguments, okay? In this example, we have two arguments. So we have arg2 and arg1, okay? So they are pushed there by the caller, okay? After that, the caller will make the call instruction, which will push the return address. So after argument 2 and after argument 1, we will have the return address, okay? I will just call it return, RET there, that's the address. Then after that, we are in the call E function. The call E will first do push EBP, okay? So that means after the return address, we have the saved EBP value, okay? Then after that, EBP eventually will point to this saved EBP value, okay? The saved EBP value, you can imagine, it's also an address, so it points to a higher address, which is last function's stack free. Okay. Then we have local variables, okay? So this is AT&T syntax here. I wrote this in AT&T syntax. So the parenthesis here is just like the bracket in Intel syntax. So what EBP points to? In a function, EBP always points to the saved EBP. Okay. What EBP plus 4 points to? EBP plus 4 points to the return address. EBP plus 8 points to the first argument for 32-bit. 64-bit obviously will be RBP plus 16, not 8. If you do EBP minus something, then you will point to something here. So that probably is a local variable. If you feel this is a little bit confusing, we will have more examples later. Okay. Let's look at this. Question?
That's a quick question.
Yeah.
So for the function calls in the previous example, is there a reason why they're different in when providing the inputs? Like, I don't know if I was reading it wrong, but it looked like it was calling instructions each time.
You have good eyes. I would say it doesn't matter for now. Okay. That's just a random example. Okay. Yeah, so it doesn't really matter there. Yeah. So let's do several quiz here. The first instruction, move what EBP minus 8 points to. The bracket here means memory. Move to register EAX because the destination is the first operand, EAX. So what we are doing here, the first instruction, what we are doing here?
The value at EBP minus 0x8 is going to EAX.
Yes, but semantically, what are we doing?
Some sort of local variable.
Yes, we're loading some kind of local variable from memory to register. Then how about the next one? Load the effective address EAX bracket EBP minus 24. What is the difference between move and LAX? Move is actually moving the data. LAX is the instruction to get the address. Okay. So EBP minus 24, still probably a local variable. We're trying to get a local variable's address, okay, in the register EAX. So those are negative indexing over EBP.
So why are we dereferencing EBP minus 24 to get the address? Wouldn't we just load EBP minus 24?
That's a very good question. So we don't have an instruction to do that. What you are saying is basically you need to do a subtract, then you need to do a move. Those two instructions.
Yeah, get that outside.
Yes. So this one, you look at the syntax, there's bracket, but that bracket doesn't really mean you need to go to the memory to do that. Okay. It's just where the Intel syntax, the instruction. Yeah. Then we have positive indexing here. 32-bit here. Move what EBP plus 8 points to register EAX. So what we're doing here? Which one? First argument you said? Yes, that's right. So EBP points to the saved EBP. EBP plus 4 has a return address. EBP plus 8 has a first argument, 32-bit. If it's 64-bit, you need to change everything from 4 bytes to 8 bytes. Then EBP plus C to EX, what is that? Exactly, right? First argument is at EBP plus 8. Second argument, EBP plus C. C is 12. There are some conventions. We do not use EBP. We could also use ESP to do that. But most of the functions you look at in this class will be EBP based. But this is hacking, right? So you probably will meet some binary that was not generated in this convention just to confuse you. So the key is to understand each instruction to say what's going on. Okay, another example. A C function to compute factorial. Simple function has a main function, has a fact function. Main function calls the fact function. Main function still takes 2 arguments. The first thing we do is we compare if argc is 2. Okay, argc is the number of command line arguments. If it's not 2, we print out the usage. How to use this? Fact and an integer, then return. Okay, so the program returns. Otherwise, it will call this print function, but actually before calling print function, it will call this fact function. It will call fact. The fact return value will be used for printf. The printf here is the factorial of this number is this. Then it shows the first argument because the command line argument is actually a string. So we use A2I to change that to ASCII to integer and print out argv1. Okay, argv0 is the name of the program. Then we are going to call the function fact and give the number, whatever number you give there to call that. Then let's look at the fact function. The fact function will have that parameter n. It will print out which fact we are calling. For example, fact 3, fact 4. Then it will print out the address of n. Okay, for 32-bit, that address will be on stack. So we are going to say the stack address for that parameter. Okay, and this fact function, then if n is smaller or equal than n, we return 1. Otherwise, we will recursively call itself fact n minus 1 times n. Okay, so this is probably you learned from somewhere else how you implement a factorial function, right? But obviously, this is not the smart way to implement this. If you took algorithm design course, you know you can do a dynamic programming to make it much faster. But that's not the point of the class. The point of the class is to show you how this works. Okay, so now, so what do we expect to say here? We're going to say a lot of printf here. From, let's say, if our input is fact 5, then we're going to say in fact 5, then in fact 4, in fact 3, 2, 1, right? Eventually. Then we're going to say the address of n. It's the same local variable for this function, but the address will be different because every invocation of this function, it will have its own local variables. And you can expect the address to be smaller and smaller to a lower address, right? So if we go to so let's first do an OBJ dump of this one to look at its binary code. So -d here means disassemble. -m here means we'll specify what kind of a syntax we're using. In this class, I use Intel syntax. Then we go to, let's say, we go to main function first, maybe. So this is the main function, and the main function eventually calls, so this is a return. So main function actually returns from here. Oh, there is a if, so there are multiple returns. Let's say, here, the main function calls fact, right? And the facts, in this case, will take some argument, but the argument is from command line. It's not hard-coded. That's why before this, we do not really say push a hard-coded value. Instead, we say moving something to the ESP points to, so equivalent to a push. We're still pushing something, but that's not a hard-coded value. Then, in fact, well, this is, we don't really need this part. We can move up a little bit. Okay. So this is the fact function. Okay. So the fact function eventually calls itself. Okay. So this is recursive. So when it calls itself, it goes back to the beginning to start execution. Okay. So that's why it's recursive. That's why this is possible, because you just execute code. Then what I'm trying to show you here is, let me see. Oh, we call that fact. So we just run the program, I guess. We run this program with 5. We run it again with maybe 9. So you can see that the first time we call it, we are in fact, and the parameter is 9. Then fact calls fact again with parameter 8, and the nth address will be lower. As you can see, this one is 80, this one is 60. So the address goes down, the stack goes down. Then after this, so after fact 1, what happens? Where do we go to? Exactly, not directly to the main function. After we return from fact 1, actually we return to fact 2, then return to fact 3, eventually fact 8, then return to the main function. Okay, what's this? Another example. This one I want to show you, also show you how do we push parameters onto stack. The function takes 5 parameters, A, B, C, D, E, add them together, that's it. In 32-bit machine, the rule is we're going to push each of them onto the stack, right? So we should push 5, push 4, push 3, push 2, push 1. Okay. For 64-bit machine, it's different. We have enough registers to pass the first 6 parameters. So that 5, 4, 3, 2, 1 will not be pushed onto stack. They will just go to those registers. Then let's say the disassembly of this. We go to the main function because the main function calls func. So it's very clear here. Main function calls func, and main function pushes 5, 4, 3, 2, 1. Then call func. That's it. The func itself is not that interesting. Then we go to the 64-bit version of this. This is a 64-bit version of the same function. Before the call function, before the call instruction, we do not have pushes. Okay, we only have move instructions. We're moving 5 to register R8D, 1 to register RDI. So the convention here is the first parameter goes to RDI. So actually it goes to RDI. The reason there's EDI here is the number we gave is very small. So the highest 32-bit will be 0. They probably reset it somewhere. So that's why we only need to move to EDI, but actually it's RDI. Then the second one goes to RSI, then RDX, RCX, R8D. Okay, so we are using registers to pass. So this one will be much faster than the previous one because this happens just in the CPU. Of course, the CPU need to retrieve those instructions from memory, but then the CPU doesn't need to move extra data from the memory to the CPU. The previous one, the push, every push, you're moving some data to memory. Okay. There are actually other calling conventions, like I said. Another one is called fast call. On 32-bit, there is a fast call convention. This one will ask the compiler to pass the first argument in the register ECX and the second argument in register EDX instead of pushing them onto stack. Okay. We do not have so many general registers in x86. That's why here we're only using 2 general registers. But in 64-bit, we have many, many more. So by default, we are using 6 registers. By default, in 32, we're not even using any register. So to use this, modern compilers all support this. Your function needs to explicitly declare this. The attribute will be fast call. Okay. So without this, we are going to use a stack to push. With this attribute, then the first 2 registers will go to ECX or EDX. We can see an example of this. Still using the global variable example. Here. Do you remember the source code? The source code is func. The parameter is 10. Okay. So we're not pushing 10 to the stack. We are moving 10, which is A in hex, to the register ECX. Okay. Because we don't have one parameter. If we have a second one, it will go to EDX. That's it. Okay. So that is the fast call convention in 32-bit machine. 64-bit version, like I said, the first argument goes to RDI, second argument RSI, third argument RDX, RCX, R8, R9. Okay. This is actually quite important later when we try to hack. Because a lot of hacking we are trying to do is to overwrite the memory. Okay. Imagine as long as it's on memory, we have a way to overwrite it. Now the calling convention put everything in registers, then we cannot overwrite, right? The string copy will not be able to overwrite the registers. That's why we need some new techniques, which was only discovered maybe 12 years ago. Yeah. So return-oriented programming, we are going to use that technique. We'll talk about this, so we can skip this. This one we already look at. So this one is also similar. 64-bit version, RBP minus 8, a local variable, RBP minus 24 in hex, still a local variable. We are moving the value or getting the address. However, if you say this one, move RDI to RAX at the beginning of the function, that is actually retrieving the first parameter because the first parameter is in RDI, it's not on stack. Or if you say before a call function, we're moving some value, let's say in register RAX to RDI, then we are actually setting up the parameter for the function calling we're about to do. Cool. Do you guys need a break? Okay. Then let's continue. We are going to do our very first attack today, or in this class. Okay. We are going to do a overwrite local variable. This is a data-only attack. Okay. The program we're going to attack is called Overflow local. Most of the functions, vulnerable functions in this class, I just name it vol-foo. So when you try to hack in midterm or final, look for that function because intentionally I embed the vulnerabilities there. Okay. We have a main function, compare the argument, whether there are two arguments, which means it takes one string as an argument. Then it will call vol-foo. Vol-foo takes two arguments. The first one is hard-coded 0, doesn't really mean anything. The second one is the command line argument string, whatever you input there. So whatever you input there could be a long string. That string's address will go to vol-foo. Okay. Vol-foo, the prototype, obviously, an integer I, then the string address, okay. Char pointer. We'll have a local variable j. J is initialized to the value of I. In this case, I is hard-coded to 0. So j will be initialized to value 0. Okay. Hard-coded value. Then we have a local variable, another local variable, which is a buffer, which is an array of characters. In this case, we're asking for 6 bytes. At a C code level, we're asking for 6 bytes. Okay. The compiler may give us more. Okay. There is no guarantee the compiler will only give you 6 bytes. The compiler will give you more than 6 bytes. Okay. Then after that, we have a function called string copy. We're trying to copy from P to buffer. Okay. Buffer is your local variable. P is whatever you input in the command line, right? Okay. So your command line argument, your input, could be very long. And a string copy will only stop when it reaches the end of that source string. Okay, that string ends with a 0. But the string could be very long, could be 2,000 bytes, which means that string copy will copy that 2,000 lines to that 6 byte or maybe slightly bigger buffer. Then what happens? We're going to override the stack. Okay? We're going to override the local variable j there. We're going to overwrite the return address. We're going to override the saved EBP. We can even overwrite the main function's return address or the function calling main function's return address. Everything higher than address could be override. Right? Okay, let's assume that doesn't happen. After string copy, there is an if statement to compare the value of j with 0. If j is not 0, we call the function print flag. If the j's value is not 0, then is still 0, then we print out I pt the full, then return. That's it. Okay. Very simple function at a C code level. Okay. But we're going to hack this at a binary level. So first, let's maybe do I see? Let me check. Oh, I have an animation there, so we can do it later. String copy. String copy, we'll just take two addresses. The first one is the destination address. The second one is the source address. It will copy whatever at the source to the destination. It only stops when the source ends with a 0. That's it. Okay. Before that, it keeps copying. So there are many different implementation of that. You can implement like this, or you can implement in just the 3 line of C code. Okay. Then let's take a look at the binary. This is the disassembly of the waffle, and to see exactly how this attack can happen. Okay. So right now, we are about to execute the very first instruction of waffle, which is push EBP. Okay. Which means the last instruction we executed was call waffle, right? And the call waffle will put the return address onto the stack. And before that, it will set up the parameters, right? So the stack right now looks like this. 2 parameters. The second one is the pointer, is a command line argument you are going to give the address, right? The second one is just I, which is hard-coded to 0. So it will be an address P, it will be an I. So we don't really know the address of P, and it doesn't really matter. Okay. Then we have a 0. Then after that, we have the return address. So now we're going to execute this instruction, and let's try to work like Intel CPU here. Instruction by instruction, we say what happens onto a stack. Okay. The first instruction is push EBP. So the stack will have the saved EBP value, the ESP, because it's a push. Push will change ESP, so ESP points to that. Then we move ESP to EBP. So now both EBP and ESP points to that old saved EBP, right? Now we subtract ESP 18 in hex. How big is that? That's 24. Okay, 24 in decimal, 24 bytes. Okay. So now the distance between ESP and the EBP, where it points to, is 24 bytes. Okay. The next instruction, we are going to move EBP plus 8, and we are going to move 4 bytes. That's why we use the D word pointer there. We move that to EAX. What is EBP plus 8 again? The first argument, right? Which is 0. So we're going to move 0 to register EAX. Remember in the source code, why do we do this? Because we have a local variable j, and we're assigning I to j, okay? This is exactly what we're trying to do that. We haven't assigned j yet, because j will be in memory. But we're moving that 0 to the register EAX. So the next step is to move the EAX value to EBP minus C, which means EBP minus C will have the local variable j, right? So that local variable j now also have value 0, okay? So from where ESP points to where EBP points to, we have 28 bytes. From this local variable is at EBP minus C, which means C is what? C is 12. Okay. So which means here we still have 12 bytes. Okay. So here, this local variable is only 4 bytes, but we are using EBP minus C, which means this 8 bytes we're not really using it. Right? So compiler chooses to do that for alignment or whatever. Okay. But we're not really using it. Then we subtract ESP again, 8 bytes. So now the distance between ESP and the EBP is 32 bytes, 20 in hex. Later you will say why we're doing that. Then we are pushing EBP plus C to the stack. What is EBP plus C? EBP plus 8 is the first argument. EBP plus C is the second argument. Okay, second argument is that string's address. Okay, the command line argument string. Okay. We are pushing that address onto the stack again. Why do we push that onto stack? Because we are going to use it somehow, right? So let's go back to the source code to say why we are pushing it. Because there is a string copy. Okay, string copy. The second argument is that address P. Okay, the string copy's first argument is that buffer's address. So we're going to push another address. Okay. by pushing two addresses in. So the first address is at EBP plus C. We push that again to the stack. So now ESP points to P. So now there are two P's on the stack. Then we are going to load effective address of EBP minus 12. Okay? And we know from the source code that's a buffer. And we are going to push that to EAX. Okay? So now we know that. So here we are setting up the parameters for the function call to string copy. Two parameters here, P and address of buffer. The buffer is actually on stack, but from that instruction we know that the buffer is actually at EBP minus 12. Okay? Then the local variable is at EBP minus C. This is 12 in hex, this is 18 in hex. So exactly 6 bytes, right? So compiler gave us exactly 6 bytes here. The beginning of the buffer to the beginning of the local variable j, exactly 6 bytes. Then we push that address. So this address, so since this is address, so this is a pointer. So this one points to here. This one points to a string somewhere. Now we are going to call the string copy function. This is a string copy function, and we're not going into that string copy function. We know what it does. It's going to copy whatever this guy points to here, okay? So that could be more than 6 bytes. It could be smaller than 6 bytes. As a user, when you call this function, when you run this program, you determine how long that is, right? That's why we could overflow, we can occupy the whole 6 bytes of buffer. We can even occupy the local variable, right? We can even occupy everything above that. Everything above that, right? Today, we are only going to occupy this part, okay? Next week, we are going to occupy other parts. And some of the results will be very surprising. So for example, if you occupy return, obviously, you can do a tag. But what if you cannot occupy return? You can only occupy the saved EBP there. Can you still get what you want? Well, the answer is yes. We're going to see that later. Then here, in this, there are 8 bytes here. No one is using it, right? Doesn't really matter. Okay. Then after we coming back from the string copy, then we have AND ESP 16 bytes. The reason is we don't really need those 2 arguments anymore, so we move ESP up. We're trying to balance the stack. Then we are going to compare J to 0, right? And J is at EBP minus C. We compare that value with 0. Okay. Jump equal, then if it's equal, we are going to jump to EF, which is here. We are going to print IPD the full. Otherwise, it will print the flag. Okay, that's it. Let's try to do this first. Then we go to the 64-bit version. Okay, let's see. Overflow. Overflow local 1. Okay, this is buffer overflow. When we run this program, I'm not giving it any command line arguments. It just returns, doesn't show anything. If you go back to the source code, you can understand why. Source code. Okay, so this is source code. We compare the arguments. If the argument number is not 2, then it just returns. So it will not show anything, right? That's why it's not showing anything. if we do just some random 1, 2, 3, 4, okay? So I give a string which has 4 characters. It will be copied to the buffer. Does it override anything? No, right? So it shows I pity the fool. If I do 1, 2, 3, 4, 5, okay? Do we override anything? Not yet. So okay. How about 1, 2, 3, 4, 6? This one is a little bit tricky. Do we override anything? Okay. What do we override? Okay. But what are we going to get here? We're getting the flag or we're getting I pity the fool? Pity the fool, okay? So this is here, it's a little bit tricky. Let me I have a marker somewhere. Let's see. Okay, we have buffer, which is 6 bytes. We have 6 bytes of buffer. Okay. Right after the buffer, so this is high, this is low. So right after the buffer, we have the local variable j. It's actually a lowercase j. And this is 4 bytes, right? So when we do this, the string here, how many bytes? Exactly, 7 bytes. And the first 6 bytes is just 1, 2, 3, 4, 5, 6. The last one is 0, okay? So after writing 1, 2, 3, 4, 5, 6, we are overwriting the lowest byte of this one, okay? However, originally, we have 0 here. All 4 bytes 0. After we overwrite, we still overwrite the 0. So it's still I pity the fool, right? So still I pity the fool. But if we do 7, we will get the flag, right? That's because we override this byte, and the whole thing is not 0 anymore, okay? Then obviously, so the first 6 numbers, you are going to fill the buffer. So the value doesn't really matter. It can be anything, right? The value doesn't really matter. And you can also run much longer, okay? But here, we run much longer. When we run much longer, we get a segmentation fault, okay? The reason is we overwrite the saved EBP or even overwrite the return address. Then when that function returns, or so anyway, eventually it will execute at a random place or garbage place where you do not have legit instructions. Then it trigger an interception to the kernel. Then kernel say will decide to kill this the process. That's why we get a segmentation fault. Okay. So that's the 32-bit version of this. I guess we don't need to debug this one because it's quite simple. So we're not using GDB to debug this one. Let's say we can go to 64 version of the same thing. Okay. Same source code, 64-bit version. Valfu, the beginning will be similar. It's just from EBP to RBP, ESP to RSP. You see the string copy here, okay? So you look for some dangerous functions like string copy. Obviously, it's not the only dangerous function. Then there's a compare. This compare is compare RBP minus 4 to 0, okay? Which means the local variable j is at RBP minus 4, okay? And the local variable is 4 bytes in this case. Then before that, string copy has 2 parameters. The first one is destination, the second one is source. And RDI has the first parameter, RSI has the second parameter. So from here you can say the source. No, we care about destination, not the source. Okay. The destination is RDI, and RDI gets value from RAX. RAX is EBP minus A. Okay. Let's see. So I don't remember the value before, 32-bit, but okay. So here we have the buffer. The buffer starts at RBP minus 8. Right? Oh, 8, not 8. Minus A is 10 in hex. Then we have the local variable J. J is at RBP minus 4. So still, even though 64-bit, the compiler is giving us exactly 6 bytes. Okay. So which means our exploit will be the same as the previous one. Right? We just need 7 bytes to override this, then we can get the flag. Same thing, if we do 6, it will not do anything, but 7, it will give us the flag. Okay. By the way, everyone will have a different flag. So if you cheat, we can catch you. We do catch people in exams. Well, I mean, if they share exploit, actually we cannot catch them. It's harder for us to catch, but if they share flags, we can catch them. Well, I trust you guys. Okay, so that's 64-bit. Now we are moving to a slightly harder one, and I want you guys to hack this one. Okay, so turn on your computer, laptop. The only difference here is we do not compare if J is 0, okay? We compare J to a very specific value. That's it. Okay. But you still need to find out where the buffer is, what number you need to put there to get the flag. By the way, we do have a way to catch people if they check the share exploit. So we check their history. In the last 5 minutes, they magically solved the four challenges and with correct, never try anything else. That's obviously a flag.
Overflow to 32, right?
Overflow local to 32.
Yeah.
Usually, one of the challenges I will give you guys source code, not everyone.
Got it. So if we're supposed to have the source code, it'll be obvious that we're supposed to have it.
I will tell you. Yeah.
I wasn't sure we're supposed to have it.
Sure. Got it? So what is the first challenge you guys encountered so far?
Instead of hard coded, it's passing like the number of arguments this
Okay.
time around.
Yes. So in command line, what you give is a string, right? It's not really the number. We are asking for that specific number, and that number has 4 bytes. The highest, most significant byte has value 12. So one way, okay, you can use Python here. You can choose Python 2 or Python 3 to send raw bytes to the program. Here is, this is command line in the shell. You first type the name of the program, then use $sign parentheses to run another program, and the result of that program will stay here as a parameter command line element for this program. Okay. So here, you can choose either one. Let's say if you do Python 2, then we can print out /x12, /x34, whatever. Okay. So that is a 1 byte text value. If you use Python 3, this is a syntax, a little more complicated, but they're the same thing. I'm not showing the exploits, but I'm showing the syntax for you here. So what are you supposed to do? You are going to send 6 bytes plus that value, right? Okay. I see some of you doing this. Say this is a program, and you do 1, 2, 3, 4, 5, 6. This doesn't matter. After this, you do, let's say 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's say if you do this, what happens? This whole thing is a string. Okay. So the buffer will be here, then 6 bytes. Okay. Then we have J here. Then J has 4 bytes. Then the first byte of J will be 1, but this is not really number 1. This is, which is 31 maybe? Yeah. ASCII value 1. 31. Is it 31? Anyway, this is ASCII value. Then 2 will be ASCII value, maybe 32. Then 33, 34. So this is not what we're asking. We're asking for 7, 8, 5, 6, 3, 4, and 1, 2. This is lower address, this is higher address. So that's why if you do this, this will not work. Who can win this? Give the first block here. You got it? I got it. Cool. You still have it. You probably do the terminal, then do history there, sheet. Yes. Yes. You can work on the 64 before. Sure. I'll use just Python to represent other, yeah, syntax represent. Okay. Okay. So how many arguments you are giving? No, 3. Come on, this is the first one. This is a name. This is the second one. This is the third one. The program only takes 2. Yeah. ASCII table. Yeah. That's the right path. There's managed. It's really right. That's when you fix it. Yes. You can change. Okay. For this one, you don't need to break. That's I'm sure you can do it. It's so it's oh, very close. The name is was this one. What is slash C? Slash C. That was slash C there. See, Louis type. Yes, I see. Yeah. Steer, getting close to what? Ah, but that's what I was doing up here. Yeah, just trying to. So basically here. But like I didn't even know I wasn't doing the high. What are you guys doing here? What have you tried so far? Okay, so what's wrong with this? You didn't write to the buffer, right? The buffer, you didn't override the buffer. Yeah. You're directly putting the number there. Yeah. Okay. Why? Because you're trying to use a SQL? Yes. Yes. You see, yes. Oh, we got 87 stuff. So it's 87, right? That's not. No, because well, we're asking for hex value 12, 34, right?
Okay, okay.
Yes. Are we getting there? You're trying to override the buffer first, right? So the buffer, right? So here you are putting that number to the buffer, 4 bytes. Then you are keep putting the number again, and on. Okay, let's see which one is it. Yeah, over local 32 byte. How many? We have probably people got it so far. We can see it here, so it's a lot of fun in the exam, so I can monitor what's happening. Okay, let's take a look. Let's look at binary first. We are trying to attack is lawful. This is actually very similar to the one we looked at before. Just the number is not 0, instead of it's 1, 2, 3, 4, 5, 6, 7, 8 hex. Everything else, they're the same. The buffer size, the address of the variables, they are the same. Right? So we still have the same picture here. We have a buffer, which is 6 bytes. We have the okay. We have buffer, local variable, J, and we're going to, whatever we input as a second command line argument will be copied from here to forever actually. Okay. So what we care is the value in J, right? So do we really care about what we put in buffer? No, but we still need, right? So we put 6 bytes of garbage, whatever, as long as that's 6 bytes, right? Now after that, we should put J, and J has to be this value. 1, 2, 3, 4, 5, 6, 7, 8. So this is a little endian machine, which means which is the most significant byte, 78, is the least significant byte. So which one should go to, this is high, this is low. So there are 4 bytes. Which byte should go to where? This one. This is a lower address. Address should have what? A significant byte, right? Which means hex 78. This one 56. This one hex 34, 12. Okay? And we're writing from this direction to this direction. Okay? So from, if you write a Python script, it will be very simple. Let's say we use Python 2. Just C. What do we print? We print, let's say just A times 6 times. Right? That's garbage. We don't care. You will fill the buffer. Then we just slash x 78 slash x 56 slash x 34 slash x 12. Okay. Then make sure you create 4 bytes, and that 4 bytes after A. Total 10 bytes. That's it. So I see you guys make some interesting mistakes. For example, this type. Instead of a /x, you write /c. Okay, then what happens? When you do /x78, this whole thing, this 4 characters becomes 1 byte, which is hex 78. When you do /c, that probably doesn't escape anything. Then it becomes 2 bytes. One is slash, one is c. And then you can check the ASCII table to say what are the values. I don't remember. Then let's say you do /x7856. Okay. What happens is this whole thing is a string. It interprets this part x78. It interprets this as 2 characters. Okay, this is 5, which is probably. So the whole thing is 3 bytes instead of what you want. So let's see. So the exploit here is like this. Say going to print 6 bytes of garbage plus 78, 6, 34, 12. So this is how you get the flag. Right? So this 6 byte of buffer is important. If you change this to 5, 4, will not work. Okay? 6 bytes of buffer is important. The value in that buffer doesn't matter. You put whatever there, use that. The order 78, this order is also important because endianness. This is the first byte you send. It goes to the lower address, so you should the lowest byte of that value. Okay, so 64-bit version actually is similar. So let's. I give you guys 2 minutes to finish this one. Then we move forward to another challenge. I hope everyone get this one first. If you finish 32-bit, you can quickly finish 64-bit. Very similar. Got it. Let's see. Yeah, some change messed up. What is this?
It'll only, right,
Let me try. If you do that, let's see. You can do the 64-bit version.
got it, yeah.
Another. Let's got it. What is here? You're trying to do what is a /x? It's a slash. That's at least 1 byte. That's just okay. Minimal syntax. So some of the programs we're going to hack in this class will not take input from command line argument. Instead, they will take input from standard input. Okay. So in that case, you need to pipe the input into the program. Okay. So in the computing system class, you wrote a shell, so you know how pipe works. We pipe into a program. So this is another example how you pipe into a program. There is another interface I want to introduce to you is instead of just write those raw bytes, you can also write Python script to hack the whole thing using a library called Pwn tools. Okay, so this is the code Pwn tool. Our system already installed Pwn tools, so you can also write code like this. You first import that Pwn tools. Then there is a variable or a system configuration, thing called a context, provided the Pwn tools. Then you can do context.binary, then elf, and name. This is going to interpret the program. The debug level doesn't really matter that much. Then you create your, let's say, payload. The payload here is bytes of garbage. So here we have 6 bytes of garbage, then plus another 4 bytes of this, right? Then you just run this program. You use the process interface to run this program. And this is an array. The first argument is the name of the program. So it's binary.path, then the payload or garbage. And after that, you can do a p.interactive to make the terminal give control back to you. Okay. So this also works. So when our exploits get much more complicated in the future, so sometimes writing this kind of exploit will be much easier, but you don't have to. Technically, everything in this class you can do just by typing simple commands in the terminal. So let me show you guys how to do this. So we are still using this one. Okay. So obviously you can only create files in temp. So you need to go to temp, then you can exploit there. Just create what should be the myself. Not really matter. Then I only use Emacs, so not, if you use Vim, I cannot really help you. Next here. So I copied it here. That is correct. So when I copy from slides, you need to change the quote here. Copy from slides, the quote is different. Okay. Then it's basically the same thing. You create this binary, then you construct this payload, then you just create this process by giving this payload as a command line argument. Then this one is common, so this one should go here. Then you just call the process interactive to get control of that. You just do a Python 3. give you the flag here. Okay, so contours also give you other information. For example, the binary. This is x86 architecture. We're using reload, which is a defense technique we will talk about later. Stack canary. You asked about stack canary. So this program doesn't have a stack canary. Non-executable stack is enabled. PIE is enabled. Then start this process. Then we get the flag. Okay. So you can also run this contour script to do that. Okay, so that is basically challenge. Oh, a little bit more information. So context is the global configuration object. That's why you set a binary there. You can set architecture. You can set many other things, but the default one will be okay. So technically, binary here. Okay. Then process is the interface to launching and controlling the process. We can send bytes to it. We can send a line to it. We can receive bytes from it, receive until something, interactive, close, and also do many other things. We're going to discuss about those interfaces when we need to use them. So far, for this program, we're not using any of those interfaces because the input is from command line arguments. That's why the input is the second item in this array here. Okay. So let's say if you are done with Overflow 2, then let's work on Overflow local 3. You don't have to write a script. Overflow 3. Overflow local 3. So this is the first challenge that I'm not providing you guys with the source code, only binary code. Doesn't really matter here. Okay. Yeah. So X here is not trying to pass anything. Because it gets overwritten. X0. Other single query. Yes, for the IP single volume. You are, that's this little say become a string, and that's actually 3 bytes, 6 bytes. Just plus, you need a plus, because that is taking the strings and it's another string. You have a forward slash there. Yes. Yes. Yeah. Yes. 57. Mistyped it somehow. Yes, so that's why you just hang. I actually typed it. I'm sure. Yeah, I just added a certain two there. It's the single constant. So print is inside that. One. Oh. You gotta print it. Second one. Third one is all transfer one. Okay. You don't need VPN here on camera. I don't get it. You're on campus. You don't need VPN. Sure. Don't connect it to any VPN. You don't need VPN here. Why? Oh, so that's not a VPN issue. That's a Wi-Fi issue. Okay. 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 I don't know why you have a Wi-Fi issue. Everyone else system is working. Okay. Let's start. Okay. Here you're not even running the program, right? It's just tab it. Tab it. Oh, you got it? Yeah. Okay. Let's take a look at this. First you will see something weird like this. Call __ x86 get PC thunk.bx. Okay, so for those things you can skip for now. So those are actually generated by the compiler for position independent code. The idea is at sometimes the code needs to know where it is when it is executing. It needs to know its own address. Okay. But modern code, they can be placed at many different places because we want to security. We want to randomize the position we place them. Then they need a way to figure out their address at runtime, and this is functions for that. So that really matters for us. Okay. So what we should look for here is how the program take input, for example. The previous program takes input from command line arguments. This program actually calls fread. So fread is file read. It's going to read from a file. The file here is actually the standard in. The file here is actually standard in. Let's see, where is that? Should. Anyway, it's reading from standard in. Then it will, let's see, here's the key. Here is print flag, right? Our goal is to make this function to call print flag. Before print flag, there's a compare. Compare not equal. Not equal. If they do not equal, the previous compare if not equal, it will jump to that place. Otherwise, it will call print flag, which means we want this compare to be equal. So here we're comparing EAX with a hard-coded value, 19CA33. Hard-coded value. Then how do we get EAX? EAX is from those instructions. There is a multiply EAX with EBP minus 10. What is EBP minus 10 again? Local variable, right? Multiply EAX with a local variable. Now, how did we get EAX here? Then we say EAX was actually moved from EBP minus C, right? So there are two local variables. Now we know there are two local variables. So let's say EBP points to here. EBP minus hex 10 and EBP minus hex C, okay, which is 12 and 16. So there are two local variables, and each of them are 4 bytes. 4 bytes, 4 bytes. We're going to multiply those two numbers together, and the result should be that 19 CA33. Okay, that should be the result. Then, obviously, our goal here is to do some kind of a buffer overflow to override those two. Then, the program will multiply them and get that number. So let's keep going up forward to see how we do it. So here, there's F rate. F rate is going to read from STD in standard input, okay? And where it is reading to? It is reading to EBP minus 20, which is great. This is EBP minus 10. Here we have EBP minus 20, so which is 32 in hex. So then we are going to override how many? 18 in hex bytes actually. So that's here you see. So that's 24. Right? That's 24 bytes. That's perfect, right? So this is 16 bytes. This is 4 bytes, 4 bytes. Okay? We're going to override. We're going to write from here. So we need 16 bytes of garbage. Then we need 2 bytes for one number, another for 4 bytes, another 4 bytes for the second number. Program will multiply them together. Same as this one, then we will print out the flag. So this is basically integer factorization problem, right? Well, let's say more to hex. Find a decimal hex 19. No. A33. The decimal number is this. Okay. Then we do integer factor. Just find an online tool to do that. Must be one. Let's say this one. Okay. The value, they don't take hex. That's why we converted decimal. Factor. So it gives us those two numbers. And those numbers are what? Are decimal numbers. And then we convert them into hex. Then we use a Python code to generate that. Right? Of course, there is another way to do this. You don't even need to convert it to hex. Just you write a script like this. The first number, decimal, the second number, decimal. Then here, there's a garbage, 16 bytes of garbage. For the calculation, we understand 16 bytes of garbage. Then we are going to convert this to a 32 bits number. That's why P32. That's the function provided by this library. Convert that. Then this one is not taking input from command line argument. That's why we're doing P in that process. P dot send. We're going to send this to the program. So either way works. Okay, work on it. I'm also trying to show you guys here. So what are those two numbers? First number is 1231. The decimal to hex. 001. The hex will be 04, say F. Next one is 1373. 1373. Vert 55D. Okay. Now we go back here. This one takes input from stdin. That's when we're trying to pipe into it. Python 2. Print. 12 bytes of garbage, right? 16 bytes of garbage. Then 8 bytes of two numbers. First number is 04, say F. So it should be say F 04 00 00. Next one is 055D. So 5D 05 00. This into the program. Say it works. It works, right? If you mess up with 1 byte or even 1 bit, it's not going to work. It's not showing you the flag. Yeah, go ahead.
Just minor issues. So I was trying the exploit.py method, like I wrote my Python script and move on, and it says that we don't have that package on the container. When I did it, it said oh, okay. Yeah, got it.
Cool. Let's move forward. We have more things to cover today. So obviously, the key to crack this one is you need to do some reverse engineering, understand what this program is doing, then know how to convert things, but by writing script, things will be a little bit easier. Okay. So what we learned today, we want to put this into this bigger picture, try to understand, because everything in this figure we're going to cover this semester. So this is the SOK paper I mentioned last week to give us an overview of all the memory tags. So what we are doing here, the very first step is we make a pointer to go beyond the bounds, right? The pointer we are using, in this case, where is the pointer? Pointer to go beyond the bounds. What does that mean? What is the bounds here? Copy to write something to the buffer, right? The bound is actually the beginning and the end of that buffer. We're not supposed to write beyond that. If you write beyond that, is not our intention. That's an error, right? And a string copy, that function has pointers that goes beyond that bound and writes things there. We have that pointer. We are going to write something. We're not reading, we're writing. After we write, we're trying to write to a data variable here, okay? We're not trying to write to a code pointer. We're trying to override the local variable j, and in Overflow 3, we're trying to overflow 2 local variables. But those are data, right? First of all, they're not code. Second, they're not pointers in this case. They're not pointing to other place, or not data pointer, not code pointer. Then we can write it to a specific value we want. In Overflow 1, we write to long 0. Overflow 2, we write to that 1, 2, 3, 4, 5, 6 thing. Overflow 3, we write 2 numbers to 2 specific numbers. Then those data are corrupted, the program keeps running, And because of this is a data-only attack. We're not attacking the control flow, which will be a different story, which we'll cover later. So this attack can also be very, very powerful. The example we're seeing today are very simple examples. Why they're powerful? Because the data you overwrite, they may be very important. They are security sensitive. The first one, the J, it controls, that variable controls whether the program will print out the flag. So it's security sensitive. It could be like authentication flag, whether this guy has already been authenticated. Right? It could be something like user ID. In the kernel, each process has a UID, group ID. That's in the kernel. If you overwrite that to, let's say, your regular user, like CTF in the platform, if you hack into the kernel, you overwrite that kernel credential to root, then you will have root privilege, right? That's still a data-only attack. So actually, we submit a paper today to CCS talking about how we use a new hardware feature to protect UID in the kernel using new features. Then there could be other many important things, flags, or even data lengths. If you can override that, you can cause other kind of overflow. This is actually very powerful for heap, which we will talk later in this case. This is another example, right? So we have a buffer, the username. Then we have whether this guy is an enemy. So this variable obviously is security sensitive. If you override this, then this guy has privilege escalation. There are some generic approaches to defeat this kind of a data override attacks. One approach is called data flow integrity. So this approach ensures that all the data in a program only flows along intended authorized paths. So what does that mean? We have a buffer there. It has a bounded size. String copy is copying data to that buffer. And string copy's job is only to string copy data to that buffer, not beyond that buffer, right? So we make sure that when string copy makes the copies, or whoever makes the copies, whatever instruction makes the copies, it has a permission to make that right. Okay. So this is a static and dynamic approach. Either compilers help and also runtime help. Usually, first do some static analysis at compiler level to figure out the definition and the use relationship. Okay, this variable is defined here. This variable is used by other statements, and no other statement is supposed to write to that variable. This can be compiler level. Then at runtime level, we are going to instrument some instructions to make sure that every write, we can do that kind of a check to say if that is legal. Let's say we are going to store some value to an address. Then the compiler will do some instrumentation. Before that store, it will check whether we have the permission or privilege to store that to that address. If not, then we detect an attack. Okay. So this is a very generic approach, and I only discuss this at a very high level because it's actually quite complicated. Okay. So that's basically what I want to cover. We still have some time, so I will let you guys to work on those challenges, Overflow 4, 5, and also this week we have a reverse engineering challenge. I'm going to show you guys the homework of this week. So this is second. Oh, I need to change my website a little bit. So the homework this week, we are going to do a reverse engineering challenge This is reverse engineering 32-bit. Then you will do overflow 1, 2, 3, which we just did. Then there are also 4 and 5. And I will be walking around in the classroom to help you guys. So hopefully you guys can solve most of this. Then this week homework will be easier for you guys. Let me update my website there.